So I think both centers are connected.
Both are? Okay, good. Let me just make sure everything is working here.
So we'll start.
All right. Good morning, everyone. First question, how did the questions I had given you go? The three questions to be solved for parallel plate waveguides. How did that solutions go? Anybody who was able to solve at least the question with different impedances? What I'll do then is I will solve those questions personally tomorrow myself, and I'll send the solutions to the instructors you have there. And you can submit your solutions to the instructors, and they can check how close you are to the right answer. Uh, so I'll give them the solutions for those three questions by tomorrow. Let's continue our discussion on the rectangular waveguides. And just before we start any new topic, again, I like to do a review of what we have been doing. We said that we are going to look for TE or TM modes. We said that again, in general, the TE or the TM modes could have all four different components of the transverse components of the electric field and the magnetic field. In general, they could have components EX, EY, HX, HY, HY. Where they're going to differ is in their longitudinal components. The TM mode is going to have a longitudinal component of the electric field, and that component is propagating in the Z direction. And because this is a component which is parallel to the conducting boundaries, this is a component as drawn in this diagram. This is a component which is pointing in the Z direction and is thus parallel to the conductors to all the conductors in the rectangular waveguide. It is going to have a sinusoidal variation in x direction and a sinusoidal variation in y direction. This conductor, this electric field is pointing in a z direction, and it has to fit at least, it has to come back to zeros at the boundaries, so it has to fit at least one lambda by 2 within the waveguide in x direction, and similarly a cut of lambda by 2 in y direction. So we can see that with respect to the origin we have defined, this function is a sinusoidal function. As I have drawn it, this is your TM11 mode. It could also have a function which is going to be something like that in x direction, and it could be something like this in y direction, in which case it would be two lobes in y, two lobes in x. Let's say this is x direction and this is y direction. Two lobes in x, one lobe in y. So this has to be TM21 mode. Then we had said, okay, the Maxwell's equations dictate that once the electric field has been determined in one direction, the other components are going to depend on that value, that they are not independent of each other, they are dependent on each other. That's what the Maxwell's equations dictate, whether it be the Faraday's law or the Ampere's law. in this specific case, we applied the Faraday's law to get various components of H, and then Ampere's law to get various components of E. And we saw that now you can have components in general in X direction, electric field in X and electric field in Y. The electric field in X direction, that electric field which is in X direction, that electric field is parallel in this direction over here, is parallel to that plate, and is vertical, is perpendicular to the side plates. So as soon as you see that, you know that this variation will have to be a sign variation in y direction. This variation has to be such that the electric field has to be 0 here and the electric field has to be 0 on the top. So this has to turn around in amplitude at least like that. So it is going to have a sign variation in y direction. And by now you must have noticed that if the field is coming perpendicular to the plates, it is going to take a cos variation, and uh, that is basically because the derivative of that field gives me the value of Ez. So because this field is perpendicular to the plates in the x plane, is perpendicular to the planes in x plane, it is going to have a cos variation in the x plane. Similarly, if we go to the the EY field on the other hand is a field which is in this direction, which is in the top direction. So it has to be 0 at x is equal to 0 and 0 at x is, it has to be 0 at y is equal to 0, the bottom plate. X is equal to 0, the side plate. This field is parallel to the side plates. So this has to be 0 at the plate here, and this has to be 0 at the plate here. So in x direction, this field should follow a sign variation, and in y direction, this field should follow a cos variation because the field is perpendicular to those planes. Based on that, if my field of EY is taking this form, the other field which is carrying the power with it, which is the field which is coupled to this field, is going to be the HX field and is going to have the same variation. Similarly, the field which is coupled to the EX field, which is not coupled but which is generating the power for the within that part, EX cross HY, that field is going to have the same variation as my EX field. So again, remember EX and HY will have the same variation in XY plane. EY and HX would have the same variation, whether it be a TE mode or a TM mode. The constants we get in front are the constants which are coming directly from Maxwell's equations. And the propagation constant is given very similar to the parallel plate propagation constant, except now because we have confinement in the second direction too, we start getting another term over here. That's the only difference to the propagation constant mathematically as opposed to the parallel plate waveguide. Similarly, now if we consider the TE mode, and in TE mode, what you have is a component which is in the z direction, so the hz component exists, but Ez is equal to 0. And then we had seen yesterday that I cannot do direct boundary conditions on HZ, because what HZ will create is going to be a current which will flow across that, some equivalent current, and we'll see today what that equivalent current is going to look like. So that HZ field can be supported. So I can't guarantee that the HZ field is going to be zero, but the EY field is going to be proportional to del HZ by del X, and the EX field is going to be proportional to del HZ by del Y. And EY field and EX field are parallel to the conductors, at least two of the conductors, those are parallel. So at those two boundaries, the derivative has to go to zero, the field has to go to zero, hence the derivative of the field has to go to zero. If the derivative of the field has to go to zero, again remember, when does the derivative, if we take a look at the sine function and the cos function, the sine function follows like that. Cos function is basically a function which is off in phase by 90 degrees. Is off in phase by 90 degrees. And where does the derivative of and the derivative of the sine function is the cos function. And not only that, where the sine function has to go to zero, the derivative of the cos function is zero. If I take a look at the derivative of the cos function, the derivative of the cos function is the slope which I see there and the slope which I see here. And I know that the electric field is going to be the derivative of my function, a derivative of my magnetic field, and the electric field has to go to zero, so the electric field has to take a sinusoidal form in that direction. And because the electric field has to take a sinusoidal form, it means the derivative of the cos of the uh, magnetic field has to be zero, which basically comes to me, which basically presents the solution that when the derivative of the function is zero, it can only be a cos function, not a sine function. So because that both the derivatives in hz in x and hz in y have to be zero, the variation in x and the variation in y are now going to be related by cos functions. So once you have done this math, you really don't need to do the maths again. Just by looking at it through the physics of the problem, you can write what the solutions are going to look like. Because the derivative has to be zero, sine and cosine are related with each other by derivatives, and the sine function has to be zero, and the derivative of my whatever my solution of hz has to be zero. And where sine is zero, the derivative of cos is zero. So it just basically tells you that the solution has to be of a cos form. So the magnetic field is going to take a value of cos and sine. Now if we now take a look at the various components which are present, we have Ex component. Ex component is parallel to the bottom boundary and the top boundary and perpendicular to the side boundaries. So the Ex field is going to have a sign variation in y direction and is going to have a cos variation in x direction. It will vary sinusoidally in the vertical direction. It's going to vary sinusoidally like that. And over in this plane, it's going to vary by a cosine function. Ey field is a field which is in this direction, and thus it is going to vary sinusoidally in x and as a cosine function in y direction. Ex and hy are the two fields which are creating the power. So the hy field has to have the same variation as my EX field. And similarly, EY and HX are coupled together, are the fields which are carrying the power in Z direction as a pair. So these two have to have the same variation also. And then the constants in front come from the derivatives and from the various terms we have in the Maxwell's equations. If you notice now, except for these constants, the field variations for the TE and the TM are very similar. It's the constants which are different, but the field variations are very similar whether it is EX, EY, HX, HY for TE or TM. How that field varies in the direction is very, very similar. All right, so this is what we had covered till yesterday. And we had seen that whether it is a TE or TM mode, the equation for the cutoff frequency remains the same. 1 by T pi, 2 pi square root of mu epsilon m pi by a square. And the TE00 mode does not exist, so there is no TEM solution. And also TM0N or TMN0 modes do not exist. The smallest TM mode is TM11. However, TE10 and TE01 modes all exist, can exist. And if A is greater than B, then TE10 mode is the dominant mode, which basically means that that mode is going to have the lowest cutoff frequency within the waveguide. This is what we had covered till yesterday. If you have any questions, let me know. If there's something which you have not understood, let me know. And then we can start looking at some current distributions within these structures. You have any questions? If you have no questions, let's start looking at the TE11 mode, and let's start looking at what that mode would look like. TE10 mode, the dominant mode. Let's assume again for the rest of the discussions, we're going to assume A is greater than B. Doesn't we're just going to assume that for the rest of the whole discussions. And let's consider TE10 mode, which is the dominant mode for the structure. For most of the applications, except for certain cases, you would be working with this mode for most of the applications. You would be normally working with this particular mode uh, uh, for most of the design applications which we have. So let's understand what this mode would look like. Again, this mode is m is equal to 1, n is equal to 0, which tells you m is in the direction of x. So there is one lobe in x direction, and n is equal to 0 is basically shouting in your face and telling you there is no amplitude variation, there is no lobe in y direction, so there is no amplitude variation in y direction. We can look at it through the maths, but this is what it basically is saying. If we go back to the various modes, we can basically put m is equal to 0 and n is equal to 0. If I put, m is equal to 1 and n is equal to 0. If I put n is equal to 0, this sine function goes to 0, and n is equal to 0, this sine function goes to 0. So it's telling you Ex is 0, Ex does not exist, Hy does not exist. However, this function here is 1, this function here is 1. It's telling you, well, Ey is going to exist, Hx is going to exist, such that m is equal to 1, and Ey is going to have one amplitude, it basically is going to be sine pi by Ax. So it is going to have one lobe, one amplitude variation in the x direction. The field is going to be pointing in y direction, but it is going to have a lobe in x direction. So putting that in maths, putting that in terms here, we know that the Ex field is Hy field. Both these fields are going to be 0. These fields do not exist. Substituting the terms, we have the Ey field, which is x, y, and propagating in z, is going to be of the form of omega mu by h square pi by a h naught sine pi by a x e minus j beta z for frequencies above the cutoff. And similarly, we have an Hy field which is going to be given by minus beta by h square, just substituting the terms in the expressions we have before, pi by a h naught sine pi by a x e minus j beta z. And we have hz terms, which is going to be h naught cos of pi by a x e minus j beta z. So if I look at the terms, you would notice that these fields almost look like the TE1 fields of a parallel plate waveguide. Basically, you have a variation in one direction, in this specific case, variation in x direction, field pointing in y direction, but the field amplitude is not changing in y direction. Nothing is happening in y direction effectively. It's almost as if it is, it's not really a plane wave because it does change in x, but it is not varying at all in y direction. The field distribution is almost very similar to what you see in a parallel plate waveguide, except now you have only a finite dimension in the otherwise infinite dimension we had in the parallel plate waveguide. If I was going to plot this field, let's say if I have a waveguide, plotting the electric field, plotted in red, again, this is what we had defined x, this is what we had defined y. Telling you the only electric field which is existing is a field which is going from between the two plates, is pointing in the y direction, and its amplitude does not change in y direction. But when I go in x direction, its amplitude changes. So just using the field distributions, as I'm going further and further away from the center, the field lines are going to be further and further apart. If I took a cut over here and I plotted what the field would look like in the x direction, and this is the amplitude of my EY field. Again, this is confined from 0 to A. If I took this blue cut and I plotted it, it would have a sinusoid variation. The amplitude at the outside is going to be 0. The amplitude is going to be highest in the center of the waveguide. And as I go further and further away from the center, the amplitude is going to drop according to the sine function till it goes to 0 on the edges, till it goes to 0 on the end of the plate. If I took a cut in another place, let's say took a cut here or took a cut at another place over here, then also when I even if I take a cut across these different planes, the field is going to look exactly the same. The field is going to be exactly the same there. It does not vary in x or y direction. It is going to remain exactly the same. The field in different the, the field is going to be the same in different values of y. Doesn't matter whether I take a cut in the center or take a cut closer to the plates or wherever I go, the field is going to be exactly the same. With respect to that field, come back to that. With respect to that field, I can show you here. With respect to that field, again, the field is going up. This is your electric field. With respect to that field, you also have magnetic field lines which are perpendicular to the direction of the electric field, but has the same variation, the perpendicular line. So basically, again, the magnetic field lines are going to be perpendicular to the electric field lines. If I have electric field in EY direction, the magnetic field lines, which are the dashed lines over here, are going to be in the EX direction, and these lines are going to be uniform in Y direction. But if the amplitude is going to vary in X direction, if I was again plotting the amplitude in X direction, the amplitude in X direction for this field is also going to be the same sinusoid form. The constant in front is going to be different, but the form is still going to be of sinusoid variation. That is how the electric field in the transverse plane are going to look like. Electric field and the magnetic field in the transverse plane are going to look like within this cross section of this waveguide. If we now go to the Z direction and plot it in the XY plane, so basically I'm taking a plane which is like that, right through the center, and I see how the field is going to go forward in this YZ plane. So there is Y on the top, there is Z on the side, on that green plane over there. Then what you're going to notice is that the field lines, as they are propagating forward, they are propagating as a wave. If the field lines, so basically, you basically now have the E minus J beta Z term showing up, which effectively is a term which is cos beta omega t minus beta z. Remember, whenever we were doing these solutions, we had assumed that the fields were going as E j omega t. And then we had taken the phasor term out, and that's why we had gotten the omega square term in our Helmholtz wave equation. But the actual field is whatever we get as E minus j beta z multiplied by E j omega t. So it is going to have a function of cos omega t minus beta z. So as you're propagating in z direction, the field is going to vary sinusoidally. So the field amplitude is going to be maximum here, then it is going to decrease to 0 after pi by 2, and then it is going to increase as cos omega t minus beta z changes, and then it is going to increase further up. This particular field was drawn for omega t minus beta z for t is equal to 0. And with respect to that, the electric field is going to change in direction, whether it is positive y direction or negative y direction. On the other hand, if I take the xz plane, the xz plane is a plane which would be if I take a cut on this plane, right at, let's say we are going at y is equal to b by 2, and this is a cut at x is equal to a by 2. If I take a cut at that plane, then you're going to see that the H field is pointing in or out of the plane depending on whether cos omega t minus beta z is positive or a negative value. And sorry, that's the electric field lines. And around those electric field lines, the magnetic field lines are closing on themselves. Remember again, the magnetic field lines have to close on themselves. And when you look at the solution over here, when you look at just the xy plane, it looks like that the magnetic field lines are never closing on themselves. So how does Maxwell's equation or del dot B is equal to 0 be true? That is coming from the fact that these magnetic field lines, remember again, the magnetic field line as we have drawn here is 0 at the outside. And if I was plotting it in the in the xz plane, you would notice that the magnetic field lines, as you are going forward in z direction, they are turning on themselves such that right at the planes over here, the field lines are 0. There's no field left at that place. And with respect to that, the electric field lines are pointing in the y direction, and in the y direction they do not change, but in z direction obviously they also have a cos omega t minus beta z term, so there is a wave term which is going through. They are changing in its amplitude in the z direction like a sinusoid wave. So that's how the distributions, the field distributions are going to look like in TE10 mode. You have questions on this? Any questions? All right. So then let's look at how the current flows, how the surface current flows. Again, remember from Maxwell's equations and the boundary conditions, the current on the surface, which is going to be a vector, is given by the normal on the surface, whatever the surface be, the normal pointing out of the surface cross the edge field. This is the boundary condition for basically effectively parallel component of H. In this case, what do we have? We have an H field which is going like that, which is going perpendicular to that direction. So we know that this H field is going to create a current on these two surfaces, and we also have, so this is the HY component, but we also have an HZ component which is a component in this direction. This HZ component is going to create, is parallel to all four electric fields. This HZ component is going to create induced currents in all these four planes. HZ will create surface currents in all four planes. whereas Hy will only create induced current or surface current in top, which is y is equal to 0, and bottom, no, sorry, top y is equal to b, and bottom, which is y is equal to 0 plates. That's the only two places where the current is going to be created. So we can look at the current on a different walls. The current for the wall on x is equal to 0 plate sorry and x is equal to 0 plate is going to be, again remember, x is equal to 0 plate is a plate here, is this plate over here, and the normal component is pointing outwards. So this normal component would be in minus y direction. So I'll have to do minus y cross hz component, and substituting the value of hz, and let's assume t is equal to 0. For t is equal to 0 term, for t is equal to 0 term, basically cos omega t minus beta z is nothing but cos of minus beta z. So I can write it as cos of beta z. So for t is equal to 0 term, this will just be minus of uh, minus y cross hz for x is equal to 0. So minus x, y cross z is plus x. So yeah, so minus x, h naught cos of uh, m pi, or m is 1. So pi m is 1 in this case. So pi by a x. Similarly, the current on x is equal to a is going to be, now the normal component is pointing upwards, so it is going to be y cross hz, and it will be x cross h naught cos of pi a by x. So what it's telling you is that when I look at the top and the bottom plates, when I look at the, I made a mistake here. What I plotted was for the top and the bottom plates. I made a mistake here. This is for actually y is equal to 0 and y is equal to b. And this should be x, because x is equal to 0 plate is this one, and this is y is equal to 0 plate, and the top one is y is equal to b plate. So this is y is equal to 0. This is y is equal to, the top plate is y is equal to b. So on these plates you have, on these plates is, so that is the term. For these plates you have magnetic field which is going parallel. The HY component is parallel too, so there are going to be two components for that field. So actually I should be still x is equal to 0 and x is equal to a. And where I need to change it is the normal components. The normal components were wrongly defined because I defined the plates wrong. So let's correct that. We have the waveguide given like that. X is equal to 0 is this plate, and x is equal to A is this plate, and in x is equal to A plate, the normal component is going to be in x direction, and in x is this plate, the normal component is going to be in minus x direction. So this, for x is equal to plate, this should be minus x, and it's minus x. X cross z is minus y. So minus of minus becomes plus. So this becomes y. And similarly, this plate would be x. X cross z is minus y. So this becomes minus y. So on these terms over here, and the only term which is going to exist is going to be cos beta z. Because when we are putting x is equal to 0, cos of pi a by x is going to be 0. So the only term which is going to exist is cos of beta z minus omega t. So what it's telling you is that if I look at the current on these two plates, the current will probably change direction. The current on one plate would be going, if the current on one plate is going up, the current on the other plate is going down on the side plates. And as you're going in z direction, the current will go from positive to negative. So if I was plotting that description, this is what the current distribution is going to look like. The induced current distribution on the side plate. So I have current going up and down like that, and it is a cost function. So where cost function in z is maximum, you're going to see maximum intensity of current. So that's why it is grouped up like that. It's grouped up closer here. And then where cos beta z is 0, you're not going to see any current going through the plane. But the current is going to be uniform along the y direction. There is no variation which is going to happen along the y direction. And the current is going to flow from top to bottom or bottom to top like that. If the current is flowing top to bottom here, on the other plane, the current would be similar amplitude but be flowing from bottom to top. That's what's happening on the side planes. Let's look at what would happen if I go now to the top and the bottom plates. Just to make sure I don't make the mistake again, let's draw it. The top plate and the bottom plate. The top plate is uh, the bottom plate is y is equal to 0. The top plate is y is equal to b. And in this case, you have the normal component is pointing in minus y direction, and on the top you have normal component pointing in y direction. Now remember, for this case, you have also magnetic field Hy present, and then you have magnetic field which is going to be Hz. Both those magnetic fields are parallel to these boundary conditions, are parallel to those values. Sorry, this is Hx magnetic field present. So you have a magnetic field H which is in the direction of x, and that magnetic field is going to be parallel to the conductor boundaries again. And because it is going to be parallel to the conductor boundaries, it is going to create its own induced current. So the current at x is equal to y is equal to 0 at the bottom plate is going to follow the function of n cross hy plus n cross hz, sorry, hx, the x component of the magnetic field, and n cross hz. When we do the terms, when we do these terms, n cross hx, n cross hx is y cross x, so I see a minus a z term on the top, and n cross hz is y cross z, so I see a plus x term on the bottom. So I see that I have a component, because of this, I have a component y cross x which is in z direction, plus or minus, depending on whether it is cos beta z is plus or minus. And I have a component here which is in x cross y, x cross z in x direction, n being y, y cross z, so that would be in x direction. So I have a current flow in a z direction going forward in my direction of propagation, and I have a variation on the wider plate. I have a variation of this current happening on the wider plate. If we calculate this, just substitute the terms, you will see we will get x h naught cos of pi by ax cos of beta z minus z of beta by h square pi by a h naught sine pi by a x sine beta z. And you notice something, and the current, so this is JSY, and the current on the top the only thing which has changed is the direction of my normal. On the bottom, the direction is in minus y direction. On the top, the direction is in plus y direction. The only thing which has changed is the direction of the normal. So this current is just going to be minus of the current I see at the bottom. If the direction changes, the cross product value changes to a negative of what the original was. So it's telling you that you have this current which is going to vary in z direction, and as it varies in z, you see there are two terms. These are off terms by pi by 2. When cos beta z is 0, sin beta z is maximum. When cos beta z is maximum, sin beta z is 0. So there would be places where the current, one of the components of the current would be 0. So you think that there should be, as I am going through my waveguide, you would now expect that there would be current would basically, as you're going forward, let's say when sine beta z is 0, at a specific value of z, when sine beta z is 0, the current is only flowing in x direction. It is flowing vertically to the z direction. It is flowing vertically out of the x. And when cos beta z is 0, I have sine beta z as when cos beta z is 0, my sine beta z is maximum, and then I have a current which starts to flow more like a sinusoid in the x direction. If I plot the current in the x direction, I have a sinusoid variation. This is what you notice over here. The current on the top and the bottom are going to make an interesting pattern where when sine beta z is 0, right over here, the current is flowing in the x direction, and the term is cos pi by ax. So the current is going to be maximum here. It is going to go to 0 in the center, and then it is going to be maximum on the other side, or the negative of the other side. So effectively, what is happening to the current is that the current is effectively flowing from bottom of the plate through this, goes to 0, and then you have a negative current coming back. Two currents coming in opposite direction would cancel each other out, and that's what is happening over here. And this current starts to create this wave pattern in the z direction as the value of cos and sine changes. So this is the place where you have the term where the current is basically flowing only in x direction. So cos beta z is 1. If cos beta z is 1, the variation is cos pi by ax. On one plate, if it is positive, on the next plate, it would be negative. On the next side, it would be negative. And if I go to another place, let's say in this plane over here, my sine beta z is 1, cos beta z is 0 at that place. And in that case, when cos beta z is 0, when this term is 0, sine beta z is equal to 1, it tells you that the current is only flowing in z direction, and the amplitude of the current is varying as a function of sine. So when I look at the walls, you notice now if I was plotting the intensity, if I was plotting the current density with respect to the center, or with respect to my axis, if I was plotting the current density at this cut over here, you will notice that the current will be 0 at x is equal to 0 and would be 0 at x is equal to a. And right at the center, the current would be maximum. But the current would be pointing everywhere in z plus z or minus z direction, depending upon whether sine theta z is plus 1 or whether it is minus 1. So that's the kind of pattern you see in the current. These are not real currents. These are not currents like if I go and pick up an amp meter, that these currents would exist. But one thing you would notice now is that effectively right in the center over here, when in this plane over here, the current is very, very minimal. Right in the center, you have a zero part here. Yes, you have a maximum part, but it's not that much. This allows us to do certain interesting things. What it allows us to do is that we can create a small narrow slot on one of the waveguides, and this would still not disturb the current flow too much. The only thing it will disturb is this one single line of current, this one single distribution going through the center, but it would not distribute, it would not change the it would not change too much into my electromagnetic field, and the electromagnetic field inside would still literally go like a plane wave. This is called a slotted waveguide, and what this allows you to do is bring in probes, and you can now start putting probes inside through that slot, and you can start interacting with the electromagnetic wave which is going inside, either to measure it, or to capture energy out of it, or to be able to excite it. A typical slotted line probe is basically a short metal probe which can be inserted into the slot, and it will create minimal distributions to the electromagnetic field for the TE10 mode only. It's only true for the TE10 mode which has that kind of distribution. If on the other hand it was TE20 mode, then the current would be maximum in the center and it will be minimum because there are two lobes. The current would be maximum in the center and it will be minimum at where the two lobes of the sine are. But what these probes allow us to do is that we can use them to measure relative strength of the electric field in the cavity, and we can even modulate the electromagnetic fields with low frequency signal, and thus or demodulate it, and thus we can start doing some communication. We can modulate the electromagnetic field. We can have an electromagnetic field generated somewhere else at a high frequency, and we can come up with a slotted probe and add another frequency, low frequency to it, to impose the small perturbation on the high frequency electromagnetic wave going through, and we can pick up that further down the road or further down the waveguide. So this distribution of the TE mode allows us to create slots within the waveguide. Next week onwards, we're going to do some microwave resonators, in which case what we're going to do is the side walls are also going to be enclosed with a conductor, and you create another confinement in the z direction, so the field is bouncing back and forth. Think of like a drum or a what is it called, the toll, which creates reflections back and forth also, and those resonators. So basically, those make very strong microwave resonators. The same way, like a toll makes a very strong acoustic resonator creating very specific beats and frequencies. Next week, when we put resonators, we enclose the Z direction too, we bring confinement in the Z direction also. Those become very, very strong resonators. And then a question is going to arise. Well, we have made a resonator, but how do we send energy into this resonator, or how do we tap energy out of that resonator? These slots, putting the slots in the proper places for a specific mode, can allow us to excite that mode or get energy out of that mode and measure the resonances of that mode. So when we come back to the resonators, I'll come back to this point again. But I wanted to show it to you today because we were doing the TE field distributions. And basically, once you realize the kind of the current you're creating, and if you made a slot somewhere on the top, somewhere here on the top, you are going to create a lot of perturbations to the current. You're going to basically cut the flow of the current completely through. Whereas if you made a slot right in the center, then the only term which you have perturbed is the current line which is going in that direction. Because the current lines which are coming in x direction are converging to be zero at that along that line, we don't create perturbations, that strong perturbations, and we can use these slots to start to excite these waveguides or measure power out of these waveguides. Any questions? You have any questions on this? Right, we have about 10 more minutes left. So what I'll do is just describe some of the terms which we have described before for the parallel plate waveguide, and these terms would turn out to be very similar for as for the parallel plate. We know that the propagation constant. So let's look at the phase velocities, the wave impedances, and the group velocities for these modes. And surprisingly or unsurprisingly, the terms would be very similar to the parallel plate waveguide. So we know that basically beta can be written as omega square root of mu epsilon. We had written this before. 1 minus m pi by a square, y minus n pi by b square.
Hello, sir.
Hello, yes?
Sir,
Sorry.
we have a doubt here.
Sure.
So you have taken x equal to 0 plane, right? During the calculation for current density.
Yes.
For x equal to 0 plane, the normal can be x as well as minus x. So why you have taken minus x in particular?
The normal is always pointing outwards of any structure.
Normal
Actually,
or what?
actually, no, this should be. No, I made a. Maybe I made a. Let me think about it a second. So the normal should be on the surface of the field. Uh, And it depends on how you define the boundary conditions. I'm just trying to quickly remember the boundary conditions. Uh, the normal component is defined into the conductor, I think. Let me just remember about. Let me just quickly review my boundary conditions. Uh,
So what I'm trying to say is for XY plane, the normal will be in Z direction, right? So in the same way, um,
yeah, so basically, you're saying that when I'm coming here on X plane here, it should be this direction or this direction, right?
yes,
And that depends on how the boundary conditions were derived uh, for the magnetic fields. I'm just going through my old notes quickly. For one thing, physically nothing really changes. The only thing which changes is where it is positive and where it is negative. If the normal is in this direction or the normal is in this direction, the only error is a negative, but we are dealing with waves, right? So, yes, at an instantaneous time, the answer would be negative of what would be derived here if the normal wasn't properly defined. But physically, that description doesn't change at all. Physically, that electromagnetic field distribution and the current distribution doesn't change at all. Just a second. Just let me just quickly go through my derivations of my magnetic field boundary conditions. I normally work a lot with electric fields, not with uh, magnetic fields in my life. Uh, so I don't remember magnetic field so much on my top of my head. But yes, the boundary conditions of the magnetic field are so the normal conditions for the boundary field are defined as uh, let's say uh, if you have medium one, medium two, then the normal conditions when you're going from medium one to medium two are defined as the magnetic field normal in the medium two. So let me just go to a new slide. So the way we define the boundary conditions for magnetic field to apply the derivations is that if I go from medium 1 to medium 2, then we define the normal in medium 2. We define the normal component in medium 2, and then I could have an H1 parallel here and an H2 parallel here. So now if I define my condition as it is written here, I can apply my Ampere's law, which is H dot dl is I enclosed. And in this case, medium 2 is your conductor, and medium 1 is the dielectric where the magnetic field is existing. So in our case, this could be Hz or Hx. And medium 2 is the conductor. So the way the magnetic field conditions, the N cross H is written, was written under this specific geometry. So when now I apply my Ampere's law, so I can go from a path like that, and basically what it's going to do is, if I go through this path, let's say A, B, C, D, A, I go from A to A over that circular path, H dot dl is equal to the current which is going to be enclosed, and the current is going to be some Js times the width of this path, the width being delta W. And H dot dl is going to be, as it is written, is going to be H1 delta W in the first medium minus H2 delta W, and this should be Js delta W. Sorry, again. My computer has started giving me. Just a second. Okay. This being cancelled out, and this has to follow your right hand thumb rule. So this tells you that the JS as it is written is pointing out of the board, because it has to follow the thumb rule. So then what we define is, with respect to how we have defined this boundary condition, this becomes N cross H1, the H in one medium, H2 in the second medium is 0, there is no magnetic field flowing in the conductor. That is equal to the current we have as it is written. So pointing out, this has to follow the right hand thumb rule. So now with respect to the waveguides, this is, think of what we have, the structure what we have is a conductor. I'm just adding some medium to the conductor. I have this conductor and I have some H field which is parallel to that. This conductor is, let's say, just to the Hz term. This is equivalent to the H1 we had, and thus the normal which has to be defined, if I was using that equation of A cross H, which has been derived for, would be a normal which is coming from the dielectric into the conductor. This would be the normal on that component. On the other plate, on the other side, now I am sitting here, Hz is sitting here, the normal would have to be on the conductor pointing outwards. So that depends on how we define the boundary condition specifically. Did I answer the question or no?
Yes, sir.
So it's back to your to your last term course when you probably had seen these boundary conditions.
Yes, sir.
It's
Studied
with
about it.
respect to that equation. Okay. I think any other questions?
So these boundary conditions are taken under conductors as perfect conductors.
As
Correct,
perfect
sir?
conductors, yes. Yes. So that is the errors you get in all these calculations. Uh, Even when we had calculated the loss for the uh, parallel plate waveguide, there was an approximation we had done there. Remember, when we had calculated the loss, we said that we had certain electromagnetic distribution, and that electromagnetic distribution was creating a current on the plate, and the current on the plate was the one which was creating the loss. But the electromagnetic distribution was calculated assuming the resistance was zero, but the loss was calculated assuming that there is a finite resistance. So these are what we call perturbations to this, and you can do the exact solution with a small with what is called perturbation theory. You first assume that the conductors uh, are fully are perfect, that the resistance is zero, and then what you do is you basically, as the resistance is zero, then you basically uh, calculate the electromagnetic field. You calculate the loss due to the electromagnetic field in the first run, and from that loss now, basically because you have a finite resistance, then you apply, from that loss you apply a small perturbation to the calculated electromagnetic field, and within 2 or 3 such iterations you are able to get to a decent solution. However, again, remember, most of these waveguides are being designed for low loss. We want to propagate electromagnetic fields through them with minimal loss. So this resistance, though is finite, is a very, very small resistance. The material chosen are such that the resistance at that frequency where you're operating at is a small resistance. Because of that, the skin depth is actually the electromagnetic field, and again, going back to your electromagnetics course, you had seen that when an electromagnetic wave is hitting a conductor, it only penetrates a little bit into it, and that is called the skin depth. And the larger the conductivity of the conductor, the smaller the skin depth is. The skin depth is basically where the electric field intensity will drop down to 1 by E, or 0.367 of the beginning electric field. That was only of the, or that was basically directly inversely proportional to the conductivity. The larger the conductivity you have, the smaller the skin depth you have, the smaller the penetration of the electromagnetic wave you have within the metal. So these approximations, these analytical solutions are still pretty accurate, even though there is an approximation that the conductors are zero resistance. Uh, you can do full calculations by putting conductance, and in fact, when you're going to high frequencies, when you're doing research in high frequencies, especially anything above 10 gigahertz, 60 gigahertz being a very interesting area of research these days, you don't do analytical solutions, you do numerical solutions. You put the actual value of conductance, because at those frequencies the conductance can drop down very quickly, So you put the actual value of conductance, and then you solve the Helmholtz equation numerically, either with finite element method or with FTDT method, which is called finite time difference domain method, or some other frequency component methods. But there are no analytical solutions for those conditions where you have to put the conductance in, become very difficult to do. They are there are no pure analytical solutions. You can only do some semi-analytical solutions, uh, which are again approximations. So for most of the applications for up to below 10 gigahertz, the approximation of conductors being perfect does work pretty well from the wave shape, from the wave propagation. Uh, it doesn't work well for losses, obviously, because this will tell you that there is no loss happening, but we do see some loss. And that is the first perturbation we do, saying, hey, um, the small resistance probably doesn't change the electromagnetic distributions that much. So let's just assume let's just take the calculations we have for the simple case and use those to calculate the loss as we had done before for parallel tape waveguide. Did I answer your question?
Yes, sir. So what are the metals that are used to construct the waveguide? What metals do you use?
Depends on a lot. It depends a lot on the frequencies. For low frequencies, meaning up to 2.4 gigahertz. Uh, for like very low frequencies, few hundreds of megahertz, it could be even steel. But normally you use either copper or brass for up to 2.4 gigahertz. For high frequencies, it could be copper with gold plating. So you have a plating of gold, but that's like really high frequencies, uh, because again it becomes expensive, right? So basically, the idea is the gold conductivity keeps on, it doesn't drop as you go to high frequencies. So you put a thin layer of gold, uh, basically above the skin depth, which is a uh, half a micron or so. So you put a very thin layer of gold on top. Uh, are you doing any lab in these cases? Are they doing any labs? But if you go to the labs, right, like look at a coaxial cable, which is your standard cable, Cat5, for example. That would be copper in the center with Teflon around. But if you plate, but if you go to high frequency, like 2.4 gigahertz cable, that would act the good quality 2.4 gigahertz cable would be copper with the gold plating on it too. So the same transmission line which you have studied before would also have a gold plating. So so that's like up to 60 gigahertz or so. You can use gold plating. When you go to further high frequencies, if you go to terahertz, which is few hundred gigahertz, normally 500 gigahertz, which is again another interesting area of research these days, because a lot of materials have direct vibrational absorptions, and thus you can use that for sensing purposes. If you go to terahertz, then any metal becomes very lossy. So the metals don't work very well. So people have been using silicon in that case, which is a semiconductor material. Uh, so people have started using silicon. So basically, so those waveguides are about 100 micron thick of silicon material, uh, and normally they'll either put it on a Pyrex glass or they'll float that waveguide in air with some supports around the side. Uh, so it again depends. The metal used depends a lot on the frequency you're operating at. Obviously, the thing is you want to be as low cost as possible, but then you don't want you want to achieve the performance. So copper, brass, If you look at in your labs, probably you're going to see lot of copper, you're going to see a lot of brass there. You may even see some aluminium, but normally aluminium is not used. Uh, uh, and then there is another material called covar. It's a uh, it's a alloy of cobalt and I forgot the exact composition. That can be used also.
Yes, sir.
But that covar is used for expensive applications where cost is not that big an issue.
Yes, sir. Thank you, sir.
All right. Any other questions? All right, then we'll stop here. I have created a slide deck. I'm almost finished creating a slide deck, which is all these equations which we have derived, but typed instead of handwritten. I'll put that slide. I'll send you that slide deck too for your purposes. And I'm doing some simulations uh, today. I'll put those simulations also within that. So basically, it would plot these fields, what we talked about today. It'll plot those fields in color plots. So you can basically, when it's red, you can see it is going to be highly intense field there. When it is blue, you're going to see the field intensity has gone down. So I'll send those things up. That would be a supplement to everything we have talked about before. Tomorrow we'll continue this discussion. I'll probably finish. Uh, I'll try to finish the rectangular waveguide tomorrow. If not tomorrow, we'll finish it in half class on Thursday, and then we'll do problems on Thursday. Uh, Question for Jaya, if you're here. How familiar are they with Bessel functions?
The students haven't. They are taught about the Bessel functions in mathematics also. So we need a introduction and
So we need
what
an
is Bessel function? What
introduction,
are the
okay.
properties?
Because one of the topics you have is circular waveguides, right?
Yes, sir. Yes, sir.
And for that we would need the Bessel functions.
Yes, sir.
So okay, then maybe
I guess
Friday's
we,
lecture would be on Bessel functions before we go to circular waveguides. Okay,
yes, sir. We need a brief introduction about
Bessel
Bessel
functions.
functions. Yes, sir.
Okay, okay.
So regarding
Alright.
YouTube channel, sir,
Yes,
have you
yes.
created any?
Uh, my my colleague is supposed to create the person who does my all these videos for me is supposed to create, but he hasn't done it yet. Uh, I'll get it done tomorrow for sure.
Yes, sir.
Tomorrow I have a lot of time. I'll get it done tomorrow. Uh, I'll give you you have I've been posting the videos on my YouTube channel. You have the link to my YouTube channel, right?
Yes, sir. We have the link, but it's better to have all things together in a channel.
Yeah, so I'll create a YouTube channel only for Soda because my has uh, 50 other videos too. But I'll put all these in one channel.
Okay, sir.
It'll be done tomorrow for sure.
Okay. Thank you, sir.
All right.